In this video, we're going to look at series and their notation. We're going to use summation notation for the first time. We're going to use the formula for the sum of the first n terms of an arithmetic series. We have a special formula for that. We also have a special formula for the sum of the first n terms of a geometric series. I'm also going to give you some other formulas that are not going to fit for a geometric or arithmetic, so we can still do the summations. And we're going to find the formula for the summation of an infinite geometric series when it exists. We're also going to solve some annuity problems. As an example, we have this couple decides they want to start a college fund for their daughter. They plan to invest $50 in the fund each month. The fund pays 6% annual interest compounded monthly. How much money will they have saved when their daughter is ready to start college? This is an application that we'd be able to solve at the end of this section. So let's first talk about what summation notation is. And basically what it is it says I'm going to sum up some bit of information and I will have some formula. And I need to know a couple things. I need to know which term to start with. So that is my lower limit of summation. This is telling me term number 1. If k equals 1, that tells me to start with term number 1. If k equals 15, then I'm going to start with term number 15. And this tells me where to end. This is my upper limit of summation. Now you'll notice that this k, we call this a dummy variable. It could be seen as n or j, and it's also going to be typically a part of this formula right here. This formula is the closed or explicit formula that you would have seen for a sequence. Now, what we're basically doing is we're taking our sequence and then we're adding up so many of the terms of that sequence. That's basically the gist of it. So when we're looking at a summation notation, here's how it's going to be wrote. It's going to be k equals some number to n. Now, the lower number could be 0, but we typically start with 1. We will not start with anything less than 1 because our inputs, as we know, for sequences have to be the numbers of 1, 2, 3, possibly on occasion 0. So we do not put in a 1/2. We do not put in k equals 52.3. We don't put in k equals -5. And that goes back to the way that we did sequences. Here is the notation for just the closed formula. It's a sub k. That's just the closed or explicit formula that we're going to be using. And then n is where we stop. Now, if we use an index here of n equals 1 to, say, 7, then what we'd see here is a sub n instead of a sub k. That is, k is my dummy variable, which is what we talked about before. Sometimes we will see this, and we've seen this in our Pre-Calculus 1 class when we were doing matrices. We've seen that when we were doing matrix operations, this is the way it was defined, and at the time I was like, what is going on? And basically, what this notation says is that for row I and column j, those two get multiplied together and then added up to go into that position when we do our matrix multiplication. So there's a place in which we've seen it before, we just never really talked about it. Is the lower limit always 1? No, it could be 0. It could be 5, but it's not going to be a negative number, and it is not going to be a fraction. So when we're asked to sum up a series, if it's already in summation notation, we need to figure out, first of all, what is the lower limit? Where do we start? And what is the upper limit? Where do we end? Then we're going to substitute k from the lower limit up to when we get to the upper limit, and then we're going to add them up. Now, if it is an arithmetic sequence, which is as the closed formula, which is now an arithmetic series, we have a formula for it. N is my upper limit. I take my first term, which is a sub 1, and my last term, which is a sub n, wherever I stop, so like the first 7 terms. And I add them together and divide by 2. This only works if I have the lower limit of being 1. Now, we can use this when the lower limit is not 1, but we do have to make some adjustments. If we're looking at a geometric series, we have a formula for that as well. This is for a geometric series in which our ratio is not equal to 1. It is our first term multiplied by 1 minus our ratio raised to the end term. So if I want to have the first 7, so I do my ratio, whatever it is, say it's 3 raised to the 7, and then divided by 1 minus my ratio. So we have formulas for those. If it's an infinite, so in other words, what I mean by an infinite, if you have the summation of n equals 1 to infinity, and this is where I see the infinite. That means I am going all the way up to infinity. If it's a geometric series with the ratio is between -1 and 1, then the formula just becomes the first term divided by 1 minus my ratio. And that's what the entire infinite series will sum up to. Here's some other formulas that you might find useful. When you have just k squared, k to the cube, k plus 1, and then if you have 1 over k plus 1. And these formulas are also useful. They're not in your book. If you need these formulas, I provide these formulas for the test, so don't worry about memorizing those formulas, but do know where to find them in the notes and how to use them. Now, if I'm trying to sum up a geometric series or a arithmetic series, the first thing I want to do is identify the first term, and if it's a geometric, my ratio. I need to confirm if I'm doing an infinite, I need to confirm that my ratio is between -1 and 1. And if it is, I'm going to use this formula. If it isn't, then it's not going to sum up to a number that is going to exist other than infinity. So we would say if my ratio for a geometric series does not lie between -1 and 1, then we say that its summation does not exist other than as infinity or possibly negative at infinity. Depends on which way it's going. So if I'm asked to find these sums, now notice that my index starts at 3 and ends at 7. So if I'm asked to find the sum, I can use the formulas up above. Now, if I decide I want to use the formula I want to use is summation of k equals 1 to 7 of k squared. And that formula we know up here is going to be n plus 1, and then 2n plus 1. So if I decide I want to use this formula is my n, which is 7. Let me see, and then it's 7 plus 1, and then 14 plus 1. So 7 plus 1, and then 14 plus 1, all over 6, because the summation I'm using is k equals 1 to n of k squared is equal to n plus 1, 2n plus 1 divided by 7. Now remember, this n is my upper index, so if my n is 7, I'm going to say everywhere I see n, I'm going to put in 7. Now, a couple of things. This starts with k equals 1. This does not start with k equals 1. So I can use this. It's totally fine to use this formula to make it easier. However, I'm not starting at 1. So I have to make an adjustment. So to make that adjustment, we have this rule that says the summation of k equals, let's do j to n of a sub k is going to be the summation of k equals 1 to n of a sub k minus the summation of k equals 1 to j of a sub k. Actually, it'll be j minus 1, because I want to stop 1 before the j. So if I decide I want to use this formula, then I have to take off the first two terms. And that's totally fine. So I could say that this summation of k equals 3 to 7 of k squared is going to be the summation of the entire thing from k equals 1 to 7 of k squared. And then I'm going to pull off my first two terms. And that's going to be equivalent because of this rule right here. Now I can totally do that, and then I could use this formula and then just take off the first two terms. The other way I can approach this is I can just start writing these out and then adding those numbers together. If you find it's easier to do that, by all means do that. We start out with k equals 3, so it'll be 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared, because this tells me to stop at 7 and start at 3. And after that's a calculator exercise, so I'll let you do that. Now the second one is looking at the second one, I know that the second example here, this one, is an arithmetic series. And I know it's arithmetic because this is a closed formula for an arithmetic sequence. So I know this has to be arithmetic series. And we have a formula for this. However, notice that I start at k equals 2. So I can use the formula if I do the entire summation and then take off my first term. That's a sub 1 is my first term. And I can totally do that. And I have a formula for that. Now I'm going to go back up here, and my formula again for the summation of an arithmetic series is this. It is my upper limit, my first term minus my last term, and then divided by 2. So this is going to be, I got to figure out what my first term is. Well, because I need my first term and I need my fifth term because that's my upper index. So to find my first term, I'm just going to put 1 into my closed formula. So it's 3 times 1 minus 1. Erase that. And then I need to find my fifth term, which is going to be 3 times 5 minus 1. This is going to be 2, and then 15 minus 1 is 14. So I found my first term, and I found my last term with the index of 5. Now, again, the formula is my first term plus my last term divided by 2 multiplied by my upper index. So this is going to be equal to my first term, which is 2, plus my last term, which is 14, multiplied by my index of 5, divided by 2. Now, all of that is just that. Now remember, my index started at 2, not at 1. So after doing all of that, I still have to take off my first term, which is the number 2. And then after that, it's just a calculator exercise for you. Now, if you don't want to use the formula, and that's totally fine, you can also do this by just putting your k equals 2 into the formula, and 3 and 4 and all the way up to 5, and add it up that way. So you can also do it like this. 3 multiplied by 2 minus 1, plus 3 multiplied by 3 minus 1, plus 3 multiplied by 4 minus 1, and then plus 3 multiplied by 5 minus 1. And then whatever that sums up to is the sum. Now, let's take a look at C. With example C, this is a geometric ratio with a 5 as a constant. Now, one of the things that we can do is we can rewrite this as 5 outside because it's just a constant and is not dependent on any of the indices. So we can totally write it like that. Now, notice how this starts with n equals 1. And when I put this in here, I'm going to get 1 minus 1, which is just going to give me 0. So 2 to the 0 is 1. Again, with this formula, or I can write it as a formula, or I can just go as 5, and then 2 to the 1 minus 1, plus 2 to the 2 minus 1, plus dot, 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 2 to the 9 minus 1. Now, in this case, it is not going to be easier to do this by each individual term. Now, the previous two examples, I can do the summation by each individual term and not necessarily know the formula or how to use the formula. This one's going to be a little more time-consuming to do that, so I think I'm going to use the formula. I'm going to go back up here, and it says, hey, if you want to find the summation of a series, and it's not an infinite series, it is going to be your first term, 1 minus your ratio raised to the n power, so in other words, wherever you end, and then 1 minus r. So the formula for this would be the first term, so I'd have to find a sub 1, which is 5 times 2 n minus 1, or 2 raised to the 1 minus 1, which is just 5 to the 2 minus 0, 2 to the 0, which is just 5. So that's my first term. I also need my ninth term. Oh, actually, no, I don't need that, because my summation formula for this, for the first 9 terms, is going to be my first term, that's 8 and the 1 minus my ratio raised to the 9 over 1 minus my ratio. So I don't actually need my last term or my ninth term. My first term is, of course, 5, 1 minus. Now my r is 2. So this is 2 raised to the 9th. And I know that's what my ratio is because of the fact this is how I identified my geometric sequence. My geometric sequence had the r raised to the n minus 1 and a sub 1. Now, if you remember, that's the way we wrote the closed or explicit formula for the geometric series. So that is going to hold true for the geometric sequence closed formula. And then it's going to be divided by 1 minus, and then my ratio again is 2. And at this point, this is just a exercise in a calculator. Number D is actually the same way. It is also a geometric. So noticing that this would be my a sub 1, and then of course this, because my dummy variable now is a instead of n or k, that would be my ratio. So once again, this would be s of 11, would be my first term, which is 64. 1 minus my ratio, which is 0.02, raised to my 11, because that is my upper index, divided by 1 minus the 0.2. And then again, that's just a calculator exercise. Now, here is where my upper index is infinity. My upper index is infinity. So the first thing I want to do is look to see, is this a geometric, arithmetic, or none of the above? Now, by looking at this, because I see 4 raised to my dummy variable of n minus 1, this has the form of a sub 1 r raised to the n minus 1. So we know that this is a geometric series. So then I'm going to look at my r. Well, my r happens to be 4. My r fails having the absolute value of less than 1. So this is not true. Because this is not true, it is not going to sum up to a nice number. Instead, it's going to sum up to positive infinity, because if I start to write this out, I'd have 4 raised to the 0, plus 4 raised to the 1, plus 4 raised to the 2, 4 raised to the 3, all the way up. And you can see what's happening is if I were to sum all of these up, it's going to sum up to positive infinity. Now you're thinking, well, what happens? What would have happened? I know your example here has a ratio that does not hold true for a summation, and that's true also for the summations of arithmetic sequences. Arithmetic sequences are also always going to go to positive or negative infinity. Depends on which way it's trending. Now, what would have happened if this would have been 1/4 m to the 1? Well, that's a different conversation, because if my ratio would have been 1/4, then the absolute value of my ratio is between, the absolute value of my ratio is less than 1, so that I would be able to use that other formula. Now, if it was 1/4, which is what this is not, I'd be able to use this formula up here that says, oh, it is going to be my first term, and then 1 over 1 minus my ratio. So if this would have been true, if this would have held true, then my summation would have just been my first term, which we know would have been 1. And if you're not sure, a sub 1 is going to be 1 over 4 raised to the 1 minus 1, which we know is 1 over 4 to the 0, which is 1 over 1, which is just 1. And then 1 minus my ratio. So had that held true, that's what would have been my summation. Now, if we are asked to find the summation write this as summation notation. They're not asking me to find the sum, they're just asking me to find the summation notation. The first thing I have to do is figure out what kind of series is this. Is this geometric? Is this arithmetic? Or is this something totally different? So the first thing I always do is look to see if I have a common difference between these. So if I'm looking at this, I went +2, then +6. Oh, I don't have a common difference. So it is not arithmetic. So then I'm looking for the ratio. Now remember, our ratio is defined as my second term divided by my first term, or my third term divided by my second term, my a sub n minus a sub n plus 1 over a sub n. So now I'm going to look to see if I have a common ratio. Now I have 3 over 1. Does that equal the same thing as 9 over 3, which equals the same thing as 27 over 9? And so we know this is holding true, and so my ratio happens to be 3. So we know that this is a geometric series. So k equals 1, because I'm assuming I started at 1. Now, for the closed formula for a geometric sequence would have been your a sub 1 r raised to the n minus 1. This is my first term. So this would be 1 times, and I don't have to write the 1 there if I don't want to, and then 3 raised to the k minus 1, because that's the dummy variable I'm using. And then it's just a matter of counting the terms. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 terms, and that is it. That's all you have to do. That's it. On part B, now this one's different because I don't know how many terms are there. So this adds an extra layer. So for example B and example C, I have to add a little bit to this. It's a little extra layer here. So to do B, I am going to again start out with, do I have a common difference? So this is 4, this is 2. No, it is not a common difference, so I know it's not arithmetic. If it's not arithmetic, then I know it's going to be geometric, probably. So let's look for our ratio. Our ratio will be 4 divided by 8 plus 2 divided by 4, which seems to be holding as 1/2. So I now found my ratio. So my closed formula, my a sub k, is going to be my first term, which is 8. My ratio, which is 1/2, raised to the n minus 1. So I found the closed formula, or I'm going to write k there actually. Use a dummy variable of k. I want to be consistent. However, what I need to do is I need to find out how many terms I have. So what I'm going to do is I'm going to set 1/8, 1 over 2 raised to the k minus 1 equal to the 0.125, because that's the last term, and I need to know when I'm supposed to stop. So the first thing I'm going to do is divide both sides by 8, so I get 1/2 k minus 1, and I get 0.015625. Now, this goes back to what we learned in Pre-Calculus 1, which is my variable is the exponent. So I know when my variable is the exponent, I can do one of two things. I can make this side have the same base, and I can set my exponents equal, or I can take the natural log or log of both sides. I'm going to take the natural log of both sides. And so I'm going to get k minus 1 times the natural log of 1/2 is going to be the natural log of 0.1505625. I'm going to divide both sides by the natural log of 1/2, and then I'm going to add 1 to it. So I'll get k is equal to, and I get 6. Don't forget I need to add 1 to both sides, so k is equal to 7. So my answer here is the summation of k equals 1 to 7, because I have 7 terms here, of 8, 1/2, k minus 1, and that's my answer. Now look at my last one here. Now again, I look to see if I have the same difference between them. So I went up by 8, and I went up by, this is arithmetic. We love arithmetic. Now our formula for our arithmetic So our a sub k for arithmetic, this goes back to this formula, the closed or explicit formula for arithmetic sequence, is going to be my a sub naught plus n times d, or I guess I'm using k, so I should probably have k as my dummy variable. We happen to know what d is. D happens to be 8, so this is 8. And then I just have to figure out what a sub naught is, and the way I do that is, if you remember from our previous sections, a sub naught is going to be our a sub 1 minus my difference, so it's going to be 10 minus 8, which is 2. We like that. So now we know what our closed formula is, and as before, I do need to find out what my my last term is, and so my closed formula a sub k is going to be 2 plus 8 times k. I'm going to set that equal to 162, so I know what my upper limit is. So I have 8k is equal to 160, k is equal to 20. So my answer is, when k equals 1 to 20, I'm summing up to the first 20 terms of my 2 plus 8k. And that is my final answer. Now, we talked about finding sums when they're infinite. So the first thing we do when we have an infinite sum is we decide whether or not it's geometric or arithmetic. Now, if it is arithmetic, we know it is not going to have a sum as a number. So it says, determine if the infinite series has a sum, and the answer is no on the first one, because if I take a look at this, this is going up by 6, this is going up by 6, this is going up by 6. This is arithmetic. Because this is arithmetic, it's going to sum up to infinity because it's going up, and so it really doesn't have a finite sum. So it does not have a sum. So the answer is no, because the series is arithmetic. Okay, so now let's take a look at the next one. The next one is, I need to see whether or not these have the same difference, and I can see already they don't. So then I look for the same ratio. So my ratio is -1/4 divided by -1, which gives me a negative is positive 1/4. Do my next one. R is equal to -1/16 divided by -1/4. This also gives me 1/4. Okay, so this is geometric, and it's infinite. And my closed formula, a sub k, is going to be -1, because that's my first term, times 1/4 raised to the k minus 1. So my summation, it would be k equals 1 to infinity of -1, 1/4 to the k minus 1. This will have a sum. Now, if you remember, it is my first term, which is -1 over 1 minus my ratio, which is 1/4, and then whatever that is what my sum is. Then, the last one before we go into the actual annuity and the applications is this one. So I'm going to look to see, am I going up by the same or the same difference or anything like that? So the first thing I'm going to do is say, okay, from 2 to 0.6, that went down by 0.4. And then from here to here, that is not going down by 0.4. So let's see, so it's not arithmetic. So let's look to see if it's geometric. So my ratio of 1.6 divided by 2, does that give me the same thing as 1.28 divided by 1.6? I'm going to get my calculator out, and I get the same ratio, which is 0.8. So this tells me that this is indeed a geometric, and the closed formula a sub k is going to be my first term, which is 2, and 0.8 raised to the k minus 1. That means my series is k equals 1 to infinity of 2 and 0.8 to the k minus 1. And we know this is going to sum up to my first term and then 1 minus my ratio, which is 0.8, and then whatever that equals is my answer for that sum. So those two did have sums, the first one did not. Now, as before, just my other example, remember I had this one, n equals 1 to infinity of 4 to the n minus 1. That, even though it's geometric, will not have a sum. Because your absolute value of r is greater than 1, and so that's why you won't have a sum. It'll go to infinity, but it won't have a sum as a number. So if any of these are on the assessment, now you know how to answer it and the steps that I took to get to the answers. That's what I'd be looking for. Here's the last one, which is the annuity. So to figure out the annuity, the first thing is you have to figure out what A sub n is, the value of the initial deposit. You need to figure out how many deposits you're going to make total, and then you need to figure out what your R value is. The way to figure out what your R value is you take your annual interest rate and you divide it by the number of times it's compounded. Now, my first example was compounded each month, so I'd be divided by 12. If it is weekly, then I take my interest rate and I would divide by 52. So it is based on, my R now is based on how many times it's compounded. So I have to figure out what my A sub 1 is. A sub 1 is my initial deposit on this example, which happens to be $50. Next thing I need to do is I need to figure out the N. Well, this tells me I have 60 total deposits. I have to figure out R. Well, R is going to be my interest rate as a decimal, and my interest rate as a decimal is 0.05, and it's compounded monthly. So this is going to be 12. So the sum is just simply going to be, following the formula, is my 50. This is the same formula as I had before. And as an interest rate, it would be 1 plus 0.05 divided by 12. This will all be raised to the 60. And then divided by 1 minus, as an interest rate, 1 plus, and then the 0.05 divided by 12. Now we can want to simplify this. We'd want to say, hey, can't we just distribute this -1 through and just say it's 0.05 divided by 12 raised to the 60? And the answer is no. Now the reason we have the 1 there, because you're thinking, why is that 1 there? Well, because the interest rate isn't just 0.05. That's not the interest rate. If you were to do, as an example, if you were to take that and multiply 0.05 times 100, that's going to give you just the interest. And the interest then is just going to be 5, right? But if you want to know the total amount, it would have been 100 plus that 100 times that 0.05. And so the total amount, the initial amount plus the interest rate, would be that 1.05. So that's why that 1 is there. And because it is an annual, we have to divide it by the 12. That's why it is 0.05 divided by 12. But the 1 is there is so that it takes into account that it is the total amount, which is the 100 plus however much is generated by the interest rate. And then you have to divide that 0.05 by 12 because it is 12. This is, as an example here, if it would have been just done for the annual instead of the annual by the month. Does that make sense? So anyways, that's it for today.